The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Electrostatic precipitation demonstrates how air ions generated by a corona discharge can be used to charge macroscopic particles, and how those particles can then be removed from the air by the applied electric field. In an electric field E, a particle having the charge Q is subject to the Lorentz force. For particles such as dust and smoke in air, their velocity is so low that even if there were much of an applied magnetic field, its contribution would be negligible. In air, the inertia of fine particles is often negligible. The electrical force is balanced by a drag force. This drag force is proportional to the particle's velocity, v, relative to the air. For example, if such particles were spherical with a radius r, this force would be the Stokes drag, where eta is the viscosity of air. The particle velocity is then proportional to the applied electric field. The particle velocity is proportional to the applied electric field. The coefficient relating the particle velocity to the electric field intensity, mu, is defined as the mobility. It is generally proportional to the particle charge, q. If these particles are the only ones that are charged and moving, the current density is the product of their velocity and the charge density rho. The product of mu and rho is an effective conductivity. Unlike the conductivity associated with an ohmic model, this conductivity is a function of a variable that is itself as much a function of space as the potential. Although the mobility formula is strictly only applicable to macroscopic spherical particles more than about 0.5 micrometer in diameter, and yet small enough that their inertia is negligible, the expressions for the velocity and current density are useful for describing both the macroscopic particles and the ions that now account for what we observe. The apparatus consists of these coaxial conductors. The outer one is essentially grounded. The inner one, this fine wire, is connected to the high voltage generator. Although it's made of glass so that we can see through it, this cylinder is coated on the inside by tin oxide so that it is conducting. For the present purposes, it can be regarded as a perfect conductor. It's grounded through this microammeter. This fine wire is stretched along the axis of the cylinder. It's connected to a positive source of high voltage. Because we only require modest currents, we can protect ourselves by having a series resistance to limit the short circuit current. The voltage is indicated by this meter. Because the wire is so fine, raising its voltage results in ionization of the air, in a hissing electrical breakdown. This discharge is confined to the immediate vicinity of the wire. With the help of this microphone, we can hear this corona discharge as it starts as the voltage is raised. It starts at just a little more than 10 kilovolts. Pairs of ions generated by the corona discharge are separated by the electric field. Some of the positive ones follow the field lines to the outer cylinder. Thus, as we raise the voltage and hear the discharge start, there should be an onset of current passing from the inner wire to the outer cylinder. We can measure that current with this microammeter. Here's the microammeter, 10 microamps, full scale. Here's the voltmeter. Let's watch the current as we again raise the voltage and listen to the discharge. We have two other evidences of the corona discharge. One is the smell of ozone, generated by the discharge. The odor is deceivingly like that associated with fresh air. You can't appreciate that, but if we turn the lights out and make the camera as sensitive as possible, we might be able to see it. Perhaps you can see the slight bluish discharge that is uniform, typical of a positive discharge. The current and voltage provide enough information to estimate the effective conductivity. At 12 kilovolts, the current is 10 microamperes. This total current is the current density at the outer wall multiplied by its area, A. The current density is in turn the product of the mobility, the charge density, and the field intensity at the outer wall. So the effective conductivity is the total current divided by the product of the field intensity and the area. The electric field in this coaxial geometry is not uniform, so if we take E to be the voltage divided by the spacing between the wire and the outer cylinder, it would seem to be a very crude approximation. However, the space charge due to the ions tends to make the field intensity uniform. So we take E as being approximately 12 kilovolts divided by 6 centimeters, about 2 times 10 to the 5th volts per meter. The cylinder area is 2 pi times the radius times a height of 0.4 meters. The effective conductivity is therefore about 3.3 times 10 to the minus 10 Siemens per meter. The electric field is 2 times 10 to the 5th volts per meter. The mobility of air ions is about 1 times 10 to the minus 4 meters per second per volt per meter. The velocity of an ion with a voltage at 12 kilovolts is therefore about 20 meters per second. The time required for an ion to cross from the wire to the cylinder to travel the radius r of 6 centimeters is about 3 milliseconds. Common smoke alarms depend on the tendency of fine particles to collect these ions. Here we have a source of smoke. Watch what happens to the current as the smoke is introduced. As the smoke enters the region of ionic conduction, the current is reduced. Let's see if we can explain this. Here, greatly enlarged, is a macroscopic particle, such as comprises smoke. Under these circumstances, it does not have to conduct much to behave as an essentially perfect conductor. Thus, in the vicinity of the particle, field lines tend to terminate on its south pole and emanate from its north pole. Ions migrating along these lines, terminating on the south pole, impact the surface of the particle. As the ions accumulate, so does the net charge, Q, of the macroscopic particle. As the particle charges, more and more of its surface sustains outward-directed field lines. As it charges, the southern window over which ions can impact the particle closes. So there's a maximum charge that can accumulate on the particle. This maximum charge is reached when the radial electric field is everywhere outward on the surface. Here's the time dependence of the charge on a particle having no initial charge. The charge saturates at a critical charge, Q sub C. This critical charge is independent of the mobility or ion density and is proportional to E sub A, the field intensity in the neighborhood of the particle, and proportional to the particle surface area. Tau is the rate with which the particle charges. It depends on the effective conductivity, mu rho, in a similar way as for the charge relaxation time of an ohmic conductor. At 12 kilovolts, we found an effective conductivity to be 3.3 times 10 to the minus 10 Siemens per meter. So our ions can give an appreciable charge to a smoke particle within about 1/10 of a second. Once charged, the smoke particles are themselves pulled toward the outer electrode by the electric field. Let's see this happen. With the voltage off and the upper end of the cylinder closed off, we'll fill it with smoke. Watch the smoke as the voltage is applied. The particles are presumably charged in less than 1/10 of a second, so the charging time cannot account for the few seconds it takes to precipitate the smoke on the wall. Apparently, the smoke particles do not move through the air with nearly the velocity of the ions, which we estimated to be on the order of 20 meters per second or more. We can see that this is so by calculating the velocity of a smoke particle. First, we approximate the largest charge that can accumulate on a smoke particle. We guess that the particle has a radius of 1/2 a micrometer and use the same average field as before. Then the charge per particle is about 1.7 times 10 to the minus 17 coulombs. That's about 100 electronic charges. It follows that the mobility of the smoke is this charge divided by 6 pi times the viscosity of air and the particle radius. The mobility of the smoke is about 10 to the minus 7 meters per second per volt per meter, about 1,000 times less than for the ions. So in our field of 2 times 10 to the 5th volts per meter, the smoke particle moves with a velocity of 2 centimeters per second, about 1,000 times slower than the ions. What we see at relatively large particle densities is particle motions that are complicated by the motion of the air itself, induced by both the ions and the particles. This is typical of practical precipitators, which are used for air pollution control purposes. The macroscopic particle motions can be made more evident by using styrofoam particles rather than the smoke. Watch what happens as they encounter the combination of radially migrating ions and radial electric field. As long as the field is on, the particles are electrically pinned to the wall. But when the field is removed, so is the pinning force. As purchased, these particles are good insulators. They're naturally sufficiently insulating that they can contact a conducting surface like the cylinder wall and still retain most of their charge. If the charge were retained on the particles, we would expect that they would stick to the wall after the field is removed. To understand what we've seen, we need to explain that these particles have been sprayed with anti-static agent, much is used to prevent electrification of laundry. So their charge leaks away after the field is removed. Our experiment illustrates the nature of two types of charged particles that are described by unipolar conduction. Of molecular dimensions were the ions generated by a corona discharge. With mobilities of 10 to the minus 4 meters per second per volt per meter, they crossed through the air between the wire and the wall with a velocity of 20 meters per second. Macroscopic particles of smoke passing through the ion flux were quickly charged to much higher levels than the ions. Because of their larger size, they still had mobilities 1,000 times less than the ions. Their velocities relative to the air were 1,000 times less than the ions. Ion impact charging of particles and the resulting electrical force explained what we saw using the styrofoam beads. These particles have not been sprayed with anti-static agent. They too are precipitated to the walls, although in a somewhat different pattern. However, now, when the power is turned off, they tend to stick to the walls. They're so highly insulating that they retain their charge. We can either think of their being mutually repelled to the walls or of their being attracted to the image charges on the walls. The mutual repulsion of like-charged particles is more evident when the cylinder is turned on its side. Once charged by ion impact and precipitated on the wall, these particles retain their charge.